Okay, today we will be discussing about the superconductivity and its applications. This is actually a very important topic. So we will be discussing little more detail in this particular topic, right? Okay. What we will plan to do is the following. We will introduce the subject with the historical events, and we'll try to understand the superconductivity. And we'll talk about the properties of superconductors, and then also superconducting quantum interference devices. That's called SQUIDs. Okay, squid also happens to be an animal in the sea. Okay, that's not the squid what we are talking about. We are going to talk about the superconducting quantum interference device. Then we will talk about the TC, JC, HC phase diagram, type 1, type 2 superconductors. There is a small mistake in the type 1, type 2 superconductor description, which I had given in the last class. I will correct it this time. Okay, and then low temperature superconductor and high temperature superconductors. Okay, what are the distinction between them? And then the fabrication techniques of superconducting wires, the various sources from where you can get superconducting wires, the cooling technology for superconducting magnets, and what sort of refrigeration system one can use, etc. Okay, this will cover more or less about the superconductivity basics and also the understanding of the superconductivity phenomenon. Okay, we'll come to the application areas. The application areas can be, for example, plasma fusion systems, then high energy physics accelerators, medical diagnostics and MRI, SQUID sensors, standards, and then MEG and MCG, magnetoencephalography and magnetocardiography. Okay, in transportation, maglev, then industrial processing. Then the high temperature superconductors is again, which is in the market now. So there are a lot of applications for that. Induction furnaces, then high temperature transformers, SMES, which is superconducting magnetic energy storage. Okay, you can store the energy in a superconductor. Then superconducting magnets, power cable, fault current limiters, superconducting motors and generators. And then I would like to discuss with you one development which IASC has also carried out in this area, which is the BHCL 200 kVA generator. Okay, this is an important thing which we have done that at our IASC. So I just would like to discuss something about that. And then there are a lot of challenges in superconducting applications, and we'll conclude this today's lecture. I hope this will cover more or less 2 hours. So hopefully we'll try to complete everything as much as possible. Okay. Now, historically, this we have seen even in the introduction to cryogenics. In 1911, Camerlingh-Onnes actually discovered superconductivity. As I mentioned, he showed that zero resistance occurs in mercury at a temperature about 4.2 Kelvin. You can see the diagram on your right side of the screen. You can see the mercury resistance suddenly drops at 4.2 Kelvin to very low values of the order of 10 to the power minus 5 ohms. Okay. In the earlier times, this was actually, although he could observe this as a phenomenon where the resistance is up to zero, he did not really worry about the applications, etc., because this transition, also is accompanied by what is called the Meissner effect, which means the expulsion of the magnetic field from the material. Okay, this was not known at that time. So he was only concerned about the zero resistance part. Later on, now we come to know that along with this, there is also a Meissner effect, which means the material entirely becomes a diamagnet. You understand what is a diamagnet material? Diamagnetic material means the material will not allow magnetic field to penetrate inside. That's the property of the material. Okay, earlier to 1980s, other metals and alloys were also found to be superconducting. People tried and they got many materials, and especially below a temperature of 23.2 Kelvin. Some examples of superconductivity are niobium titanium, niobium 3 tin, etc. These are known as low temperature superconductors. Okay, because for making them superconducting, you require the cryogenic fluid, liquid helium. Okay. In 1986, J.C. Bednarz and K.A. Muller, they discovered the superconductivity in oxides. So it was at a temperature around 35 Kelvin, but then extensive research in the worldwide had uncovered many more oxide-based superconductors, and their TCs are up the order of up to 135 Kelvin. Okay, there are still a lot of research is going on. People are trying to find out whether they can get superconducting materials right at room temperature. Okay, people are trying to still working on these problems, and because there is a lot of interest in making sure if you get a superconductivity at room temperature, then you don't need any coolant at all. Okay, so it has a lot of advantage in getting such materials. Now, the materials whose transition temperatures are above 35 Kelvin and below about 135 Kelvin are known as high temperature superconductors, are known as HTS, high temperature superconductors. So please understand. So these, for the high temperature superconductors, you can just use liquid nitrogen as a coolant, because nitrogen boils at 77 Kelvin. So it becomes much easier for people to use liquid nitrogen for getting superconductivity in these materials. Okay. Now, how do we understand the superconductivity? First of all, we know the metals decrease in their resistance value or at low temperature. For example, copper or platinum, for example, you start with a particular resistance value at room temperature. If you keep on decreasing the temperature, resistance also keeps on decreasing, and ultimately it comes to some stable value. Okay. For example, the case of platinum, it comes to some stable value around somewhere about 25 to 30 Kelvin, constant value. Okay. So this is because of the impurities which are present in the material, and they offer a finite resistance. Okay. So the resistance due to the phonons, etc., they gradually drop because the temperature is going down, and ultimately the resistance is monitored, is covered only by resistance occurs only due to the impurities of the system. So you get a constant resistance. But there is, in some metals, for example, the resistance suddenly drops to zero at a specific temperature. That temperature is called the critical temperature or transition temperature. So at that temperature, the resistance suddenly goes to zero. So if the resistance is zero, it means that there is no voltage drop for if you pass a current through that zone, then there is no voltage drop because resistance is zero. Because V into I is, for example, voltage is nothing but R into I, resistance into current. And since the voltage is not there now, because voltage is zero, the power loss also is zero, because voltage into current is the power, and that power loss also is equal to zero. So if you just look at the way in which superconductivity occurs, electrons, for example, normally flows in a conductor, and where there is a lattice atoms which are arranged, and the lattice atoms, for example, the core, if you like to call it, the core atoms are positive ions, because the electrons are all moving and the core atoms are positive ions. Now, the flow of electrons is somewhat difficult. The reason being, the electron, although it may try to flow through these materials, they are at time, because the electrons are all negatively charged, each electron repels the other electrons, right? Okay. So they occupy distinct energy levels energy states, and because of the fact that they are what are called fermions, their spin value is off. So they are called fermions. Okay. So what really happens? So if you suppose imagine the electrons are flowing from one location to another, it is first getting attracted by the positive ions, which is the nucleus, and then it is again, as it moves because of its velocity, it is getting attracted by the next positive ion and so on. So gradually they move through the lattice. The electrons move through the lattice. Okay. But what happens is at temperatures close to 10 Kelvin, or you can say the transition temperature, the two electrons combine together to form what are called Cooper pairs. These Cooper pairs are known as bosons. The Cooper pairs, because now the electrons are all joining together. So the spin value now for these electrons will be 1. Half plus half, the spin values are 1. So the bosons, they can have many identical states. The energies for bosons can be many identical states. Now, because of the fact they are combined together, okay, they do not have any hindrance through the lattice while flowing. Okay, they do not have any hindrance for the flow through the lattice, and so they very easily flow through the lattice without, so that is resistance is 0. There is no hindrance and therefore resistance is 0. So this is causing what is called superconductivity of the material. Okay. So what really happens is the pairs are such that they do not have any interaction with the lattice. Okay. In the theoretical formulation of superconductivity, people say that the electron, one electron combines with the phonon, one electron interacts with the phonon of the lattice, and then again that interaction couples another electron. So therefore we have what is called the Cooper pair interaction with the phonons, which is causing the superconductivity. Okay, what happens at higher temperatures then? So as you raise the temperature, for example, above this Tc, the pairs of electrons are broken, the Cooper pairs are broken because of the thermal energy, and therefore the superconductivity is lost and the metal becomes normal. Okay. So please understand, now when the electrons are individual, they are forming fermions. When the electrons are together, they form the Cooper pairs, right? So, and the Cooper pairs can easily flow through the lattice, and therefore there is absolutely no resistance for the flow of electrons within the material, right? Okay. Now, what are the basic properties of superconductors? One is we know that zero resistance, just now we mentioned. And because it is zero resistance, there is a large current carrying capacity. Okay. Because any amount of current can flow through this. Okay. It also has the exclusion of the external magnetic field. So there is no magnetic field that can penetrate into this material. So this is what is called Meissner effect. So I think you can see a picture here. In this picture, in this place, for example, this is the material through which the magnetic field is flowing. Here, in this case, the temperature is much, much greater than the critical temperature. And once it reaches the critical temperature, you see the magnetic field lines do not penetrate and they just diverge, go out only completely. Okay, this is what you see here. Okay. Now, there is also another important property of magnetic flux quantization in the superconducting ring. Okay, this happens for what you call squids. Okay, and in a superconducting quantum interference devices, there is a flux quantization. So what exactly is this? I'll try to just, whatever we can understand, we'll try to explain in that flux quantization. See, when you have a certain, you know, a squid is consisting of the superconducting quantum interference devices. There are two superconductors and separated by an oxide layer, which is called the Josephson. So this forms superconductor, oxide superconductor forms a, what do you call it, Josephson junction. Okay. Now, two such Josephson junctions, one can form a loop, and you can pass a current through this, through which a certain amount of magnetic field can be started with this one. Some small magnetic field can be there in this one. Okay, now what happens is if suppose due to some reason I tried to pass an external magnetic field, if the device is going through an external magnetic field, what really happens is the external magnetic field is now tries to induce a current in the system. Okay. Now the superconductor adjusts such that originally there are certain number of flux lines are trapped with the ring. It exactly matches the same number of flux lines in the ring. It does not allow. So what happens? The current adjusts such that the same number of magnetic field lines are held in the same place. So the squids are such that they can now measure precisely the external magnetic field, or in other words, because of this, the squids are capable of detecting or detecting extremely small magnetic field or magnetic field quanta. Okay, that is possible by the squids. This is because of the fact that the superconducting lines, actually the superconducting external magnetic field is now modified by the superconductor adjusts the current such that the same number of lines are now modified, or the same number of flux lines are coupled with the system. So this exactly what is happening, right? Okay, let's go to the next, this one. Okay, there are some applications which are shown here. For example, you can have a superconducting magnet, or this will be the sort of the conventional electrical cables for carrying a current, whereas a superconducting current cable is only this much. So because of the fact that you can carry large number of superconductors. Okay, this you can see a man is totally lifted off, is standing over this, is lifted off because of the repulsion between the superconducting magnet and the person. And the person is having, of course, a magnetic plate at the bottom of his leg. Okay. Now, this is the squids. Many number of squid sensors are used for measuring the brain signals. So this is one of the applications. Okay. Okay, here I think whatever I told you is discussed here. I'll just read it through. A squid refers to superconductor quantum interference device. It measures extremely small magnetic fields of the order of flux quanta. It consists of two superconductors separated by a thin insulating layer, and that forms two parallel Josephson junctions. The current enters, now splits into two parts because there are two loops, the two arms of the loop. So let us say the IA and IB. There is a flux which is inside the magnetic flux, certain magnetic flux inside the loop. Let's say that flux is called phi. So you can draw an electrical diagram for this. In the electrical diagram, what is shown. Suppose if the external flux is modified, the loop enables only integral flux quanta. That is, it maintains the same amount of flux. So now the screening current adjusts such that the same number of flux quanta are trapped inside the loop. So the screening current now alternates, this way that you can see here, it is alternating like this. And the maxima between the two flux points, the current maxima between the two is actually referring to the flux quanta. Okay. So application of extremely small magnetic field detection is possible by the squids, and they are useful for measurement of brain signals in magnetoencephalography, as well as the signals from the heart in magnetocardiography. Right. Okay, there are a large number of application areas. As you can see, you can go from low field region to high field region, or low field, no magnetic field to high magnetic fields. In the low magnetic field, for example, superconducting cables, transformers, then induction heaters, okay, superconducting fault current limiters, motors, generators, then silicon crystal growth, magnetic separation, maglev, electric aircraft, etc. Then superconducting magnetic energy storage, MRI systems, fusion reactions, then high field magnets, NMR, and then accelerator, etc. Because All these things require more and more magnetic fields and more energy is required. There are a large number of application areas like scientific research, and then medical, transportation, industrial applications, then energy related applications, etc. Okay. Now you should concentrate on this particular diagram. This is called TC, JC, HC phase diagram. So superconductivity exists within this diagram. This diagram is current density is plotted on one axis, magnetic field is plotted on the other axis, and temperature is plotted in the third axis. Now the superconducting region is the one which is inside this phase diagram. Okay. Now we said that when I lower the temperature of the material, then it becomes superconducting below a particular temperature called transition temperature, which is TC. Very good. Fine. Now I can pass a current through this. If I pass a current, I cannot pass any infinite, because the current, what it will do is, the current will also generate a magnetic field in the system. Okay, any current passing through a conductor will generate approximately a magnetic field surrounding the conductor. So now what it says is that you can pass a current up to, or the current density, we can say current per unit area, which you call it as current density, and this current quantity will be limited to the JC value. That is this blue line, this blue envelope top point. That's your JC current value. That is, any current below this you can pass, but not beyond that particular. Okay. Now, it also happens that because you are now generating a magnetic field, that magnetic field itself will try to destroy the superconductivity. And what is the maximum value of magnetic field that it can possibly have, either generated by its own current or generated by an external magnetic field, is Hc. So now you have the superconductivity exists when you have the temperature below the critical temperature, when you have the magnetic field below the critical magnetic field, and when you have the current density below the critical current density, right? So there are three basic parameters which will try to improve the system. Please note this. So superconductivity exists within this phase diagram, and you can say from 0 to Hc or 0 to Jc or 0 to Tc, that is the zone in which superconductivity exists. Okay, this is very important to understand, because this will decide our understanding of superconductivity. Okay, there was a small mistake in my earlier talk. Let me make it corrected here. Now you can see type 1 superconductor. It is the magnetic field on the y-axis and temperature on the x-axis. And this is what is called the type 1 superconductor. Okay, in the type 1 superconductor, what happens is, this is the point where there is no magnetic field. Okay, now as you keep on increasing the magnetic field, this location keeps on moving upwards here, and the temperature, so the maximum value of critical field can be only 0.041 Tesla. So there is a clear boundary between the superconducting zone and the normal zone. Okay. So please note that the superconductivity exists at lower temperatures and at this magnetic field values on over this source, right? Okay. Now, so the this particular temperature where there is a zero magnetic field is the TC of the system. Okay. Okay. What about the for example, we take a type 2 superconductor. It's a niobium tin. So what happens is, in this case, you have a transition temperature as before. Okay, maybe TC is about 18 Kelvin. Okay, and this portion, what you are seeing, this dark blue color, is similar to the dark blue color of the mercury one, what we have seen. So this is a complete superconducting state. Okay, there is also a light blue colored zone, which shows there is a what is called a zone where in between these two is called a mixture of normal and superconducting zones. Okay, how do we understand this? What really happens is, if I try to, let us say, decrease the temperature, then what happens is I can pass a magnetic field. I can put this inside a magnetic field. The magnetic field does not penetrate 100%. Okay, if it is a small magnetic field, suppose we apply a magnetic field, the magnetic field penetrates, say up to some value here, it becomes a completely penetration. But suppose I apply extra magnetic field, when the temperature is below 18 Kelvin, then what happens is the magnetic field will be there, okay, but it will be dispersed in the normal zones. Okay, so you have a mixture of normal and superconducting zones. And this is possible. That means the system is possible to have a mixture of normal and superconducting zones up to a maximum value of 24.5 Tesla in the case of niobium-10. So please understand that it's possible to have every year. So in other words, suppose I have a niobium-10. I operate at a temperature of, let's say, 5 Kelvin. So you can see here, I can have a magnetic field generated almost up to about 24 Tesla. It is possible to do a magnetic field generation up to this value. So this is the type 1 and type 2 superconductors behavior. Okay, let's move on to the next one. The development of superconductors over the years is shown in this diagram. You can see temperature in Kelvin on the y-axis, and then the year of discovery is shown on the x-axis. So people started with mercury. That is the very first discovery of camelopardalis. Then came lead, niobium nitride, okay, vanadium nitride, vanadium silicon, niobium tin, niobium germanium, etc. So as the year moved further and further, the temperature of the superconductivity, the transition temperature, also was increasing. I am looking at only the red dots, okay? Now, these were somewhere around 2000 people are able to discover superconductors of magnesium boride. That is somewhere the temperature, transition temperature around 35 Kelvins. In 1986, Bernard Muller actually created they got the, they discovered the superconductivity in oxide semiconductors. So immediately this blue dots, as you can see here, lanthanum, barium, copper oxide, ytterbium, barium, copper oxide, and then bismuth, strontium, calcium, copper oxide, etc. Lot of these materials have the transition temperatures above 77 Kelvin. Okay, so they can become superconducting directly with the liquid nitrogen, using liquid nitrogen. So this is one of the important discovery. So now you can very clearly see that the development of superconductivity has improved, has increased the transition temperature to liquid to that above liquid nitrogen temperature. But what is known is also that these high temperature superconductors are anisotropic. They are not isotropic in structure. That means the current flow in different directions can be different in such cases, right? Okay. Okay. I will now discuss about how exactly the superconductors are prepared. How do you get to superconducting wires, for example? Okay, so what we do is we start with a copper can. This is I'm first talking about the low temperature superconductors. You can get many kilometers of superconducting wires. Okay, commercially available these days. Materials like lead, niobium nitride, niobium tin, niobium germanium, etc. are now prepared. They have TCs less than 25 Kelvin. Okay. So what is the methodology? The methodology is, first you have a copper can, inside which you have a niobium barrier, inside which you put niobium titanium rod. Okay, so these things go one into the other. This is the outermost one, this is the next one, this is the next one inside. So now you make a billet, total billet. Okay, this is the total item. So the total item looks something like this. Then this one is now cleaned. You do the cleaning process, you make sure that there are no impurities, etc. After cleaning process, you do an electron beam welding to adhere all these parts together. See, they are all three separate materials. Now you make an electron beam welding such that EB welding such that the material is totally together. Next, what you do is you do the extrusion process, okay, in a small opening. So now this is a single material. Now extrusion process will make sure that you get the rod of smaller diameter, and then you draw this, and then you get many such extrusion rods. So now the cross section of this will be looking like this. Okay, the typical mono cross sections will looking like this. Next, what you do is you assemble all of them together again. All these mono they cross assembled together, and the assembled version again is put inside a copper can, and then you do the extrusion process further. Okay, sorry, I come to the other one. So then you do the extrusion process again. So you make what is called multi-filamentary low temperature superconductor by the entire process. Okay, please. This is a very, very important process. So you are able to get a multi-filamentary superconducting wires, low temperature superconducting wires. These have a transition temperature less than 25 Kelvin, and you can make many kilometers lengths of wires by this process. There are large companies, many companies, American Superconductors, for example, is one of the companies who are able to give you these superconducting wires. Is that clear? Is it okay? Hello? Hello? Are you people listening to me? Hello?
Yes, sir.
Okay. Is it clear now?
Yes, sir.
Okay, very good. Let's proceed further. Okay. Then comes the high temperature superconductors. I mentioned the lanthanum barium copper oxide, ytterbium barium copper oxide, and then you have bismuth, strontium, calcium copper oxide, etc. Titanium barium calcium copper oxide, then mercury barium calcium copper oxide, all those things. So you can see here the transition temperatures in all of them are somewhat or above 77 Kelvin. And therefore, with the liquid nitrogen, you can get a superconductivity. I'll show you this video once again. I hope you might have seen it earlier. So you can see here, this is an ytterbium barium copper oxide. This is just a magnet. And this one is going to put on the top is that room temperature. Okay, nothing is great is going to happen. It's just going to sit on the top. Okay, right. Now you cool that material with liquid nitrogen, the process of cooling it liquid nitrogen. Once you cool, the material has become superconductor. Now, if you try to keep this material on the top of that, because it is now a perfect diamagnet, it's does not allow the magnetic field to penetrate and the magnet floats. So this has a lot of applications. The applications are magnetic levitation, maglev. Okay, so these are some of the, so you can, he is showing some that you can have so much gap between the material and the magnet. Okay, and the magnet can be oriented in different positions. Okay, there are, see, you can put it on one side or you'll put it on the other side and so on. So this is also possible. Okay, then next what he does is when the temperature is sufficiently warmed up, when the system is sufficiently warmed up, he will be in a position to take out this and then place it on the, from here taken out from liquid nitrogen. So the material will gradually warm up, and once it warms up, now it is losing superconductivity. So the magnet will come and sit on the top of the material, right? Now this latter, lifting of the material has been possible because of the magnetic field coupling between this material and the magnet. Because of this, it is possible. How does the magnetic field couple? It's because it's a type 2 superconductor. Okay. In a type 2 superconductor, magnetic field lines can penetrate into the material. Okay. So you have 100% superconductivity, then there is small zones of superconductivity along with the normal, and then there is no superconductivity, that is 100% normal magnetic field penetrate. Okay, fine. Now we come to how do we prepare the superconducting wires for high temperature superconductors. There are generation 1, first generation wires, or second generation wires, etc. are available now. For example, in the first generation wire, you have bismuth, strontium, calcium, copper oxide. So these are a lot of filaments. You can see they are all in the form of filaments, and these filaments are embedded in a silver alloy matrix. So the thicknesses are like this. The width is 0.01 inches and the breadth is 0.16 inches, and the length, of course, you can have any amount of length. So this is prepared and supplied by American Magnetics Superconducting Corporation, and these are what is called generation 1 type of superconducting wires. In the next generation superconducting wire, people have, for example, with the terbium, barium, copper oxide, the base is like this. The alloy substrate is at the base. Over that, you have a buffer layer, then superconducting coating, then the noble metal layer is all done. And this is the latest, or this is the generation 2 type superconductor. Now, this is again supplied by American Magnetics superconductors, and this is a second generation system. Now, it has these designs are all are made sure they are prepared such that they are improved, they give you improved performance at a lower cost. Okay, how does one produce the 1G type of superconducting wire, high temperature superconducting wire? So what is done is we start with the precursor powder production. Okay. Now then this powder production is converted into a billet. You seal it inside a billet. Okay. Then you deform it. When you do a deformation, you are trying to reduce the thickness of this into smaller dimensions. Many of them are joined together. You make a rebundling. Okay, again into an housing, and then that is again deformed. Okay, so you get multi-die deformation that happens in this. Okay, then in part 2, what you do is this multi-die deformation is microstructured engineering. It is rolled and then stored in the form of a tape. And the tapes are now ultimately heat treated. And once the heat treatment is completed, then you have high temperature superconducting wire. Okay. So the initial wires are prepared without heat treatment, and then the last part is the heat treatment to make sure that you get the right composition of superconductivity required for superconductivity. Okay. Now the status of 1G wires is that the key application requirements are performance is 15,000 amperes per centimeter square. So you can see the superconducting wire arrangement. Then the strain tolerance is greater than 0.2%. The design value is for 0.015%. It can be useful for magnetic fields up to 3.5 Tesla, and the temperature is of the order of 35 K is required, and all the other factors are 100% tested. The current status is it is available as a 100% tested material. The width is 4.85 mm and multiplied by 0.305 mm. Okay. The fatigue strength is validated by NRL and NHMFL. Okay, and it meets the required specifications, right? So you can see some sample superconducting wires shown here. Now we go to the development of 2G wire fabrication, that is the second generation. Again, we start with the substrate production, that is extrude and draw the billet, roll into final dimensions, then polycrystalline, recrystallize to final dimensions, and then it is collected on the rolls. On this one, we deposit the buffer. Okay, it's all some chemical process deposit the buffer, and YBCO precursor is coated on this material, and then it is allowed to decompose. So when you do the decomposition, then you conversion to YBCO, and then RAM to oxygenation phase, and then oxygenation ultimate finally stick. So now you have the procedure like this to prepare the wire. That means initially the wire is prepared, then it is oxidized, right? Okay, then you can see here in this photograph, in this view, there are several layers are shown here in this one. So copper is set on the topmost, top and bottom of the copper layer. And there are many other layers are there in the intermediate zone, sorry. Okay. Now the supply of the high temperature superconducting wire status are like this. Some sources are Supercon INC MA, American superconductors, Oxford Instruments, then American Magnetics, etc. A lot of people are able to give you these superconducting wires. Now, American Superconductors is one of the leading manufacturers of the wire, and the world's first commercial high temperature wire plant is now in operation since January 2003. Now, this is now facilitated 1.4 million meters per year and has a capacity almost up to 20 million meters per year. So one of the plants of American Superconductor is shown here. Okay. Now let us look at the critical current versus magnetic field at different temperatures for the superconducting wire, for the high temperature superconducting. What is shown here is that on the x-axis you have the magnetic field, on the y-axis you have the stabilized current, and these are plotted for different values of temperatures. Okay, so what you notice here is the following. Although my superconductivity is available at 77 K, its current carrying capacity is rather small because it is quite small, so it can develop a magnetic field only some small value. Okay, suppose I take the same superconducting wire to reduce the temperature, say from 77 to 70 to 64 to 50 to 35 and finally 20 Kelvin. Then what happens is the magnetic field, what it can take up is much higher. Okay, and the current carrying capacity, current carrying capacity also improves, and therefore the material tends to take more current. And because it takes more current, it is able to generate higher magnetic field. So the performance of the high temperature superconducting wire improves at lower temperatures. So with the same superconducting wire, I will be able to have larger magnetic field if I reduce the temperature to lower values. Okay. Now, what are the cooling technologies that are available for high temperature superconductors? There are a lot of refrigerators which are available commercially. And for example, you can use either liquid helium, or you can also use cooling by a cryocooler. Both are possible. Okay. And for HTS and motors, for example, the temperature zones are in the range from 20 Kelvin onwards, some 10 Kelvin to onwards. Okay, so you have a temperature range from about 30 to about 55 Kelvin for HTS and generators. And if you see the commercial off-the-shelf refrigerators are useful in these zones. For the low temperature systems, normally one uses liquid helium because that is quite effective and people use the, so these are the possible cooling technologies available. Okay. Now, high capacity single stage GM crack cooler, they normally produce in the temperature range from 20 to 40 Kelvin. Okay. And they have been improving over time also. So for example, the cold head and the compressors are shown here. This is actually a model of, I think, Cryomec, if I am not wrong. Okay, they have a mean time between failure. It is better than 9 years. Okay, so this is a typical refrigeration system suitable for high temperature superconductor. Okay. Now let's move on to the application areas of superconductivity. So I think this is the important areas, various areas of superconducting applications we are going to discuss now. Okay. Okay. First, let us talk about the plasma fusion systems. Okay. Now, what is meant by fusion? Fusion is a reaction between the, what shall I say, the nucleus to produce, when the two nucleons combine together, they form a nucleon with a higher mass number, and in the process, they produce energy. Okay, fusion is one of the energy production process that happens in the suns and stars. And for example, the sun's core temperature is of the order of 15 million degrees. Okay, that's a fairly large temperature. So what happens is at these temperatures, hydrogen nuclei fuse together to produce helium. And in the process, it gives you energy. So the reaction can be characterized like this. Deuterium plus tritium will give you helium plus neutron plus energy. Okay. And now this reaction is going to happen at a very high temperature. And there is no possibility to have a normal vessel to have this reaction conducted. Okay. Now, what happens is if you want to have the plasmas generated and the reactions to take place, you require what is called external magnetic fields. You essentially require a magnetic cage because this was conceived by a Russian scientist and this is now called tokamak. What is a tokamak? It is a confinement device just based on magnetic fields. So what is when you have combined deuterium and tritium, they are all charged particles and they form helium and neutron and they'll give you energy. And these charged particles can be trapped inside a magnetic field only. So if you can have a magnetic cage, inside the magnetic cage, the charged particle can move around. Okay. So that is called a tokamak. Okay. Now, there are typical tokamak will have the following. A typical tokamak will have what is called the toroidal fields and the poloidal fields. The toroidal fields are the fields which is shaping in the form of a D. Okay. And the poloidal fields are the ones which are black in color, which will, it's on the top as well as the bottom. Okay. So what happens is within this the so-called toroidal poloidal magnetic fields, then the plasmas will be able to stay within this under right conditions. So the plasma reactions can go on within this area. Okay. So large superconducting magnets are used in this case, and they try to create both the poloidal and magnetic field and toroidal magnetic field. So poloidal is the field which is on the top, this fellow. This is your poloidal fields, and toroidal fields is the form of D-shaped arrangement. Okay. Now, internationally, there is a program which is going on and known as ITER, ITER, International Thermonuclear Experimental Reactor. This is going on, and it is located in a place called Cadarache in France. Okay, and a cross section of this the cross section of this particular system is shown here in this diagram. Okay, and you can see a empty channel through which the plasma reactions will take place. Okay. Now, as far as this particular fusion reactions are concerned, and this ITER is a thermonuclear experimental reactor system in which is actually conceived by many countries, and India also has become one of the countries. India has joined also in this particular program, and now because of this, they are experimental reactor. They try to produce some energy, and this energy will be tested, will be found how much is the energy that's able to produce, etc. The very first reactions, etc. This more of experimental nature. Okay, and the India actually is supplying some cryogenic items, as in its contribution will be in supplying some cryogenic items for this particular program. Okay, I think the first beam, which is expected to happen somewhere in 23, 24, etc. Right? Okay. Let's come to high energy physics accelerators. What is high energy physics accelerator? The accelerators are nothing but they are also known as particle accelerators. And these particle accelerators try to give a lot of energy to the particles. By the very name, what it implies, it is able to give you large amount of energy to the particles to accelerate them, right? So they use both electric and magnetic fields for their operation. They accelerate the particles to very high energies, and their collisions generate newer particles. So when they generate newer particles, then this will be useful for research. And for example, Large Hadron Collider, LHC, this is located in Switzerland, is one of the largest, powerful, 27-kilometer long powerful particle accelerator with a circumference of almost 27 kilometers. Okay, and you can see inside this some photographs showing you in a tunnel, the accelerators are all, coupled together. I mean, this accelerator pipe is going through this tunnel. Okay. The rings of particle accelerators are made from superconducting magnets, arranged like beads on a necklace. Okay. And protons with the energy of 7 × 10⁻12 electron volts are made to collide, and their collisions are detected by the very big giant detectors, right? So now this video shows you the working of a particle accelerator. I hope sound will be there. And in any case, you can just I think I can skip the introduction. Are you able to hear this? I'm not sure. Are you able to hear this sound? Hello?
No, sir.
Okay. Okay, I'll send you this video. Actually, I have to actually enhance the volume. Let me try whether I can. Oh, sorry. Sorry. Actually, I made a mistake. Yeah, okay. You please see this. I will try to send you the video so that you can hear it yourself. Okay, I think I have been able to show you this video, but the sound part I'm not able to improve it further. So we will see again. I will send you this video so that you can see yourself, right? Okay. I will take a break here before we start the next topic. Is that okay with you? Hello?
Okay, sir.
Yes, sir.
We will come back in about 5 or 7 minutes. See, what's the time now?
11.
11.
Is it already 11 or slightly less than 11?
Less than 11.
10:15.
10:15.
Okay. Okay, no problem. We will come back at 11:05, right? Okay.
Okay.
Are you people back now?
Yes, sir.
Yes, sir.
Can we start? Is it okay?
Okay.
Yeah, but it's not working. That's why they changed it. Join this meeting. Okay, welcome back. We will now talk about the other applications of superconductivity. We will first discuss the medical diagnostics and MRI imaging using superconductors. Okay, magnetic resonance imaging, or known as MRI, has become the gold standard in diagnostic medical imaging. You can see an MRI system in which a patient is laid horizontally and inside a magnetic field. Okay, that magnetic field will be of the order of a Tesla. Okay, and it is a very safe and powerful system and uses superconducting magnets. So it adds a lot of energy efficiency in the system. Now, MRI is able to provide tissue features which are normally not visible by X-ray images. So MRI often eliminates harmful X-ray examinations. So these MRI systems are better. MRI actually uses what is called the proton resonance frequencies. So for example, an MRI image is shown here of the skull and of the human being. And you can see the almost internal sections, etc. And what in an MRI they do is they introduce the person into the magnetic field and scan the proton resonance at different orientations and thereby generate a total image, complete image by the three-dimensional arrangements, generate a complete image of the total system. And by this way, you will be able to get the sectional images which can be reconstructed to a total image of the skull. Okay. So that way MRI is useful to detect the problems or special, the locations where the malignancy has occurred, etc. These things are possible to see in an MRI. Okay. Coming to squid sensors, standards, etc., and the magnetoencephalography and magnetocardiography. So this I already discussed with you earlier. Squid sensors are ultra-sensitive detectors for magnetic fields, and they are able to detect extremely small magnetic signals. Okay. So I explained also, for example, the Josephson junction, which normally has a screening current, and within the loop, a certain number of flux lines are all trapped. Okay, if I apply an external magnetic field, then the flux current varies such that the same number of magnetic flux lines are trapped. And therefore, you are able to see the variations in the external magnetic field. For example, squid sensors are used for detection of, let us say, defects on materials. Okay. And you can, so the entire squid, it looked something like this, only uses such a small squid. These are squid sensors which are located. And this is actually the squid sensor. The rest of it is all electronics around that. The squid sensors again hold the record of sensitivity, and it is also used in many radio astronomy observators worldwide, etc. They use the Josephson junctions, acts as a frequency to voltage converter, so they are useful for voltage standards. Okay. For example, NIST USA has developed the AC voltage standards for which are internationally available for comparison, right? So these are something that is one of the applications. There are other applications are magnetoencephalography, MEG, and magnetocardiography. Very high sensitivity of the squids has enabled the development of magnetoencephalography. For example, in the picture, you see a helmet, a big size helmet, I should say, used on the skull of the patient surrounding the head. Okay. So you can see here, they will detect the magnetic signals from the brain in a totally non-invasive manner. And the squids are also the basis of imaging the heart, the magnetic field behavior in the heart. It is called the magnetocardiography. Now, it is able to provide info on the electrophysiological activity of the heart, including the detection of the coronary artery disease. Coronary artery disease also possible to be detected using the magnetocardiography, right? Okay. Let's look at the applications in transportation. What about the transportation sector? In the normally, in the 21st century, electricity is now taking a new look as the basis for powering the transport system. We already see, for example, there are many electric vehicles which are on the road. For example, electric cars or electric two-wheelers, etc., which are now being used by many people. Okay, the reason for using these sort of things is, first of all, to prevent pollution, and also factors like electrification is the advantages of electric systems and the increasing cost of oil. Okay, and in this area, magnetic levitation is one of the very suitable arrangement of transport, because you can have a high-speed transportation with almost zero friction. So you can see here the normal conventional electric transportation by normal electricity, but the system runs on rails. So there is a friction. Okay, but in this one, for example, you can see the electric car, but it is supported above the ground because of the superconductivity. Right. So how does this work? You can just have a look at this video. I don't know whether the sound is there. Yeah. So now you see how it is working. So you have a track which is made up of NSN, okay, and the magnets are actually floating in between, okay, over that, and now you are able to see this. Okay, this again another car which is based on superconductivity. Okay, the superconducting magnets. Right, I think this will be enough for us to understand. Okay, we'll go to the maglev trains, high-speed trains. For I'm sorry if you are not able to hear what he is talking about, but just try to understand this. Okay, I think this goes on a fairly long time. I think I will stop here. We'll move on to the next one. Okay, we will consider now the industrial processing of superconductivity applications. For example, we normally use white paper for writing. And if you see some of our old papers which you have used, so if you keep them, for example, for several years, you find there is a coloration on the paper. The color of the paper becomes somewhat darkish. Okay, so it looks as though it is somewhat soiled. Okay, the paper becomes, I would say, brownish. I cannot say even brownish, somewhat clayish, more like a clay color. Okay, light clay color. So it reaches a darkish behavior. It has a darkish appearance. Okay, so why it happens over time? Because of the fact the normal clay material which is used in paper and ceramic products, they have certain amount of impurities, particularly magnetic impurities. Okay, normally the kaolin is a clay material, white clay material, which is used for this paper production and has an annual production of approximately $5 billion in USA. It contains a ferromagnetic and paramagnetic impurities. So they act as color centers and they should be removed to achieve required brightness of the final products. Okay. So they are very, very fine small particles and they have to be removed. How do we remove them? To remove them, you use a magnetic field. Okay, because they will get attracted to the magnetic field and therefore they can be removed by a magnetic field. So you need what is called a magnetic separator, and this can be done by using large superconducting magnets along with high magnetic field gradient magnetic fields. Okay, for example, in this picture, you see industrial low temperature superconducting magnetic separator is shown here. Okay, this sort of system uses liquid helium. Okay, and along with, because of the liquid helium, a superconducting magnet is inside the liquid helium. So the magnetic field is generated. You can also have gradient field magnets, and these gradient field magnets are able to separate out the impurity, the so-called kaolin impurities, paramagnetic impurities and paramagnetic impurities from the clay. Okay, so for this, actually, you have to design a large size superconducting magnet. Additionally, the gradient type magnets also have to be designed. And for example, this, as far as my knowledge goes, this has been one of the programs of BHEL Hyderabad. They had tried it at some time back. This was along with, in collaboration with other companies in Kerala for developing the magnetic field, magnetic separators for the clay materials. Okay, right. Now let's look at the high temperature superconductor applications. High temperature superconductor induction furnace is one of the important applications. It's a non-ferrous induction heaters have shorter heating times and are higher efficiency than the conventional induction heaters. The induction coils are normally made up of high temperature superconductor material, carry current, they carry the current instead of copper conductor. Now, in place of copper conductor, you use high temperature superconducting material. The power ratings of these systems are ranging from about 0.25 megawatt to about 2 megawatt, and has revolutionized aluminum, copper, and brass billet heatings. So, for example, in the photo, you can see a high temperature induction heater, superconductor induction heater. So, because of the fact that you have to pass large currents, and these currents will be sent through high temperature superconducting material in this induction furnace. Okay. I was mentioning about the high temperature superconducting transformers and also superconducting SMES. See, conventional transformers using copper as a conductor always loses a certain amount of energy because of the fact that it has some resistance. In place of that, if we use high temperature superconducting material for the transformers, so they are very compact, efficient, and also handles high power ratings in the system. And therefore, you are able to have, they can be cooled by liquid nitrogen as well. Small scale superconducting magnetic energy storage systems, or in other words, SMES, they are based on low temperature superconductors, and they are in use for many years. They are used to enhance the capacity and reliability of the conventional power grids. So as you can see, magnetic energy gets stored in large magnets, and when this magnetic energy will be dissipated, then they become useful to take care of conventional power grids. So useful for industrial, large industrial user sites with a sensitive high-speed process to improve the reliability and power capability. I'm not in a position to go into the details of the working of this SMES, etc. here. Maybe interested people can just have a discussion on this. And incidentally, the high temperature superconductor based magnetic energy storage systems are also is being worked out or being tried out by several industries. Okay. Now coming to magnets, there is a scope for using high temperature superconductor magnets for many applications. For example, right from 1996, 200 kilojoules SMES magnets have been built, and for beam switching, 0.7 Tesla magnets are built with high temperature superconductors. 7.5 Tesla warm bore superconductor magnets are also built by different companies. Largest swept field solenoid has been built with high temperature superconductors. And 3 Tesla magnetic separator, 0.5 meters warm bore superconductor magnets have been built. Okay. These have happened over years, right from 1996 to 2004. Okay. Now, some special typical magnet systems, for example, 18-inch bore, 36-inch long, one of the largest HTS magnet, lightweight and highest in magnetic moments. Coil generates a peak field of 1 Tesla at 35 Kelvin. Advantage is this, it's just cooled by a cryocooler. Okay, continuous field variation is possible at 1 Hertz, and it is delivered by American Superconductors to Navy in 2002. Okay. Now, BISCO 2223 magnet designed for continuous operation. This magnet generates about 3 Tesla field in a warm bore operating at 35 Kelvin. Okay, it is again cryocooled and useful for magnetic separator applications. So, for example, the person is showing you this high temperature superconductor magnet. Okay, there are a number of programs of high temperature superconductor magnet programs. In Central Japan Railway, Maglev, Brookhaven Accelerator Program, the Forschung Research Center in Germany, in Karlsruhe, Nuclear Science Center in India, that is now it is called IUAC, it is known as IUAC, it is in Delhi. Okay. National Institute of Fusion Sciences in Japan, Pan-Technic Ion Source in France, Tai-Yang Research, NASA, USA, Wang NMR insert in USA, cryomagnetics. Then there are a couple of other things, for example, including CERN, current leads, developments, etc. are there in Switzerland. Okay. Another important area is the high temperature superconductor power cables. Okay, what is the advantages? Suppose you use a conventional cable, it carries a certain amount of power. If you use a power cable, cryocooled cable, then it can certainly take a more amount of power through the same cable. But if you change over to a high temperature superconductor, then the power cable can have large amount of power with zero input power. Okay, zero input current. So therefore, zero input power, because you are using high temperature superconductor, there is going to be no voltage drop, so there is no power dissipation. So powers capable of 3 to 9 times or compared to the copper cables is possible using the high temperature power cables. The wire generates high temperature wire cables, enables core geometry that provide low conductor resistance and low inductance. And it's also suitable for the environment compatibility, underground placement, no electromagnetic field, thermally independent of the environment, and it can use nitrogen as a cooling fluid for this. For example, 2 programs are shown in this photograph here. 500-meter cable test site in Yokosuka in Japan, and Long Island, New York, USA also has been using a particular, developing a particular program. East Garden City substation have been using this. Okay. Now again, high temperature superconductor power cable programs are there in all over the world in different places, right from USA to Korea, China, and Japan, and so on. Right. Now, another important area where the superconductivity, high temperature superconductor has been used is what is called the fault current limiter. What is a fault current limiter? See, normally, when suppose a device can take a certain current, a conductor can take a certain amount of current, only that much current should be possible to be shown. If you pass excess current through the same material, then what happens is there is going to be a damage to that particular current carrying cable, right? That's what will happen. Now, in case a large amount of current is flowing through an electrical system, automatically there should be a way to prevent it. Okay. So such a device is called fault current limiter. Current is limited. Excess current is automatically limited. Okay. The core of this device is a superconducting material with zero resistance below its TC. So what you should do is you should install it inside of the current path. So for example, you can see the high temperature superconducting fault current limiter device. Okay, this should be installed in the current path. Under normal circumstances, it does not affect your current flow because it's a HTC material. Okay, it will be cooled to low temperature, so the current simply flows through. Okay. Suppose if the current exceeds a certain value, what happens is the quench occurs. Then because this fellow cannot take that much current, so the quench occurs, the superconductivity is lost. So suddenly there is an electrical resistance that appears, and because of the large electrical resistance, current through that pathway is cut off. Okay, large current is cut off. So the short circuit current is automatically now limited by these fault current limiters. So high temperature superconducting material fault current limiters are useful since we need to use only 77K for obtaining the superconductivity. You don't need, let's say 4 Kelvin, or you don't need to use liquid helium for the fault current limiters. That's the advantage of using HTS fault current limiter. The fault current limiter applications are in locations such as bus tie, IPP interconnection, transformer feeder, closing open loop, etc., close open loop, etc. There are a number of programs which are taken up by Nexon, Siemens, and then Beijing superconductors, Korea, also many places, and Israel. Okay, Ricor also is one of the companies where this fault current limiter development and applications are taken up. Now we come to another topic called superconducting motors and generators. Now the superconducting motors are very useful for HTS marine ship propulsion. Okay, the reason for this is they are smaller and compact and somewhat lighter, and electric propulsion systems of ships enable more flexible arrangements and HTS motors therefore are used for this purpose. Okay, and in the power generation sectors, the superconducting power generation, superconducting generators are useful. They normally the central core, which is the rotor, is generally made out of low temperature superconducting material, conductors, and therefore they actually are made of low temperature superconductors. The cost benefit for such systems will be there only if your overall power generation value is greater than 5 MVA values. Okay. Now in the picture you can see here the marine ship and also the type of motors which can be useful, HTS motors, which are useful for the ship propulsion. Here you see the superconducting generators in this photograph, and the cost benefit happens only when the power generated is greater than 5 MVA. Okay. Now, HTS rotating machinery have been done by several people, several industries like Rockwell, Reliance, Siemens, American American superconductors, GE, then again Siemens and GE and so on. So many different industries over a period of time have been trying to make HTS rotating machinery. The advantages: 2 to 4 times reduced weight, better efficiency, and lesser reactive power. Okay, higher reactive power and low noise systems are possible because of this HTS, conventional rotating machinery now using HTS system. There are a number of programs which are there all over the world, and right from 5 megawatts to very high wattages of 36.5 megawatt and so on. I would like to bring before you 2 developments. For example, BHEL Hyderabad 200 kVA generator program and BHEL HTS motor programs. I would like to bring before you just to show you what has been this type of systems. Now, if you look at the HTS motor or a generator design, multi-phase synchronous air core motor is generally used. HTS is used where there is a DC rotor field. The rotor is vacuum insulated and it's cooled by a suitable refrigeration from a stationary frame. Low reactance due to large air gap is a possible, and removal of the iron core teeth yields higher efficiency. Higher current density yields also higher power density. So these are the advantages. For example, in this figure, you can see a picture of a photograph of the actual, motor or a generator. And this is the stator coil. And this fellow is the rotor coil, which is attached. It is cooled by the cooler module. It is trying to be cooled by the cooler module. So the output shaft is somewhere here. Okay. And this shows you the air core HTS and the conventional core HTS sort of systems are shown here. The magnetic field line distributions are shown. Okay. Now, in the BHEL 200 kVA superconducting generator, which was developed by BHEL Hyderabad, now again we have a superconducting rotor, and this is the stator coils. Okay, on the upper part. I'm sorry for the poor quality of this particular slide. This is almost about it's about 25 to 30 years old. Okay, that's because of that. And now there is a component here, I think number 7, which is called the helium transfer coupling, which was built by us in IISc Bangalore and then integrated with the generator developed by BHEL Hyderabad, right? Okay, the more details are shown here. What is the item? The item is able to see, you have a rotating machinery which requires liquid helium, and the liquid helium, once it goes inside, it converts it to, it takes the heat and then warms up. Then you get cold vapor of helium gas. That cold vapor of helium gas has to come out and it will be collected in the static environment. So the liquid helium has to go from the static environment to the rotating environment, and then vapor helium has to come back in the same path from the rotating machinery back to the stationary environment. So in between, you require a device which will convert from the stationary environment to rotating environment and vice versa. Such a device is called the helium transfer coupling, which was developed at IISc. So what does it contain? It contains 4 numbers of clearance seals here. And then it contains also what is called the ferrofluidic seal, which will separate out the cold fluid, the incoming fluid, and the return gas. Okay, and also a set of bearing, conventional bearings, which has been used in this place. Okay, and the overall system will be like this. So there should not be any impurities in the system, gas that is coming back from the rotating machinery, and therefore you can use exactly the same gas directly for the helium liquefier and produce the liquid helium out of that. Say, for example, this is the total structure which was developed by the BHEL Hyderabad. So you have a helium liquefier which is able to liquefy, which produces helium in a storage vessel. Okay, and its own water cooler, water chilling unit, and then L10 pre-cooling plant, etc. are all there. Okay. Now this is the storage tank for helium. Now a part of it, cold gas, is sent to the, the liquid helium is sent to the superconducting generator. It cools the rotating part, and the cold gas, what is coming back, is collected and then enters the gas bag where it is again compressed. And this compressed gas is stored in a cylinder. And from the cylinder, it is taken back into the helium liquefier for liquefaction, So, and the process continues, right? Okay. Now coming to the industrial high temperature superconducting motors. These motors are pretty efficient, 97.7% efficiency, and normally they have a 1/3 reduction in its volume and 40% reduction in losses. Say, for example, Carey 100 HP motor is shown here, this sort of size. Okay, and 5000 HP, 1800 RPM motor is this fellow. Okay, and similarly, the fish ship propulsion 5 megawatt, 230 RPM motor is shown here. Okay. What about the cooling systems for all these units? Now, the cooling system can be either liquid helium, or it can be also directly cooled by the cryocooler cooling systems. So normally cooling is done by either GM coolers or Stirling coolers. Cryocooling systems are used. Helium in that case is used as a medium, and it is done at a pressure about 4 bar. Circulation is achieved by what are called cold circulators, and many cryocoolers have to be used in parallel for this purpose. So now you can see in the picture, okay, the all-storm motor testing is shown here, and which consists of 4 cryocoolers whose outputs are collected together and they try to they try to pass through the rotor. The cold gas pass through the rotor and then cools it and returns back as warm gas. Okay, helium gas, whatever that is needed additionally, they are all added additionally in the system. So this is useful for cooling a 25 megawatt motor cooling system of, I think there is a mistake. It says 1 kg, it's wrong. Okay. Now, as we mentioned earlier, the typical advantages of using high temperature superconducting motor is, first of all, it is quiet, large, it has a large, higher efficiency, lower operating cost, smaller volume, and it's also certainly lighter. Okay. Now, now the typical cooling systems, for example, are shown here. They're similar to conventional system. For example, this showing you no special equipment is required to maintain or handle the rotor. Stator is the same for as for a conventional machine, and the cracular based systems are much more convenient because you need not have any interruption of the thing for maintenance and so on. Okay. So cryogenic cooling system maintenance procedures are well established in the MRI and high vacuum industries. So it is well known. So you can just automatically understand and automatically utilize this cryogenic cooling system for these purposes. Okay, now what are the challenges in the area of superconducting applications? In the case of low temperature superconducting system, you have to minimize the heat load that is coming from external sources, and you have to maximize the fluid helium flow through the low temperature superconductor. So you must ensure helium leak tightness, and you should have the appropriate vacuum is needed in such cases, right? Now, in the case of high temperature superconducting systems, people are now trying to look forward to long lengths of superconducting wire in several hundred kilometers of lengths of superconducting wires. And as you also know that the high temperature superconductor has got an important, I would say, disadvantage. It has one of the important disadvantage, namely it is anisotropic in nature. First of all, people are trying to understand how to convert it to, how to handle this anisotropic type of superconducting wire. And also it causes a disadvantage in bending, the minimum bending radius of making superconducting magnets. People are still trying to understand this. Okay. Another important thing is how to increase the current density, okay, of JC of the superconductors, so that with the same superconducting wire, you will be able to have large magnetic fields. In the area of cryocoolers, one should have cryocoolers which have long performance times with minimum maintenance schedules, etc. And also you should minimize the spares required for the maintenance. One other thing is, for all this you require trained manpower with adequate knowledge to make a proper design of the systems, okay, and also to take care of, to introduce corrective measures whenever there are some difficulties or problems occur in the operation of these superconducting devices. Okay, as far as I know, I would like to conclude my talk with the following information. The superconductivity is a very, very important area. By virtue of zero resistance and Meissner effect, there are many, many applications in this field. Electric power for increased power delivery, storage, and fault finding. Then transportation sector for magnetic levitation, superconducting motors and generators. Diagnostics and medical being MRI, NMR, R is missing, sorry. And then MEG, and MCG. High energy physics towards particle accelerators, Large Hadron Collider, fusion systems, etc. Then under industrial processing, we have seen the magnetic separators, induction furnaces, etc. In instrumentation sensors, so standards we could see, radars, all those things. And high temperature superconductors, you require very long lengths of wires. When they are available, many more applications are also will be possible over the years. Okay. I think that's all I have to say. I thank you very much for the patient listening. And so we have completed the topic on superconductors by this lecture.